our next topic is electric field. Let me just make it a little more zoomed. Okay, so next is electric field due to an electric dipole. Electric dipole on its equatorial plane. Okay, so let's start with this new topic. So in electric field due to electric dipole on its equatorial plane, first let's understand what is an electric dipole. We have already discussed it before, but let me just remind you that if we have a pair of a positive and a negative charge, so let's say this is plus q and this is minus q over here, and both of them are separated by a distance 2a. Because we take the separation from midpoint, that's why we are assuming the separation to be 2a, right? And equatorial plane, that's a new term here. Equatorial plane, how do you define? Any point on the perpendicular bisector of this dipole. Perpendicular bisector means a line which is perpendicular to this dipole and perfectly 90 degree, and it is splitting this dipole into two equal halves. So that is A over here and that is A over this side also. Let me make it as A. Now, sir, this equatorial plane will be infinite. You can choose any point. So let's take a particular distance as r. This r is the distance separation from the midpoint of the dipole, right? Now let's figure out our directions. So we know that positive charge. Now positive charge, the electric field is radially outward in all the possible directions, right? But what we will do here is we will just draw a line joining the point at which we are finding the field like this, and along this particular direction we will find it outward. So this is our electric field due to the positive charge Q. Now electric field due to the negative charge, how will you draw? So simply draw a straight line and towards the charge, exactly. So electric field will be in this direction, E minus Q. That will be our electric field. Now if you have two vectors like this, one vector A and another vector B over here, then we know that the resultant of A and B will be along the line passing through the diagonal using parallelogram law of vector addition from 11th. If you know that, that's fine. If you don't know, just remember that two vectors are aligned like this, then this will be the resultant R, right? So we will make use of the same concept over here. If EQ is in that direction, E minus Q is in this direction, then our resultant of both of them, that will be pointing in this direction. That will be our electric field E net, or the total electric field. Okay. Now if such a scenario is there, then how do you find the total net electric field? So for that we should know the angle between E minus Q and E plus Q. That is this complete angle. But that would be tricky if you try to figure out the angle like that. Better way will be like they have done. You can solve it using that theta also, but that will require a little bit of maths. So we will not do it because that's not in our NCERT. But we know that this is our angle theta over here, right? So if we assume that this is our angle theta, let's use Pythagoras theorem. So let me call this as A, let me call it as B. We know that, and let me call it as O. Let's see that AO is nothing but A. OB is nothing but A. And OP we can see it is R. So if we use Pythagoras theorem, this is nothing but root under R square plus A square. That will be our hypotenuse, right? And similarly PB will be root under R square plus A square again, right? Yeah, using Pythagoras theorem. So if PAB is a triangle with two sides equal, then the angle opposite to equal sides will be equal. So this will be angle theta, right? So both angles are theta. If this is theta, then we know that this will be theta because this will be corresponding angle. To whom? E net is parallel to AB, right? So if E net is parallel to AB, then that will be corresponding angle. And if this is theta, then this will be also theta, that is alternate angle to same thing. Yeah, E net is parallel to AB, so alternate angle. So that will be theta. Okay, great. So we have already found our angles. Let's now see how to simplify. We will make use of our simple concept of 11th standard, that is resolution of vectors. Sir, what is resolution of vector? Let's simply draw an axis over here. Let's say this is our axis. Okay. So, and wait, let me just make it better. let me just make it here. This is our straight line over here, and this is our y-axis, and this is our x-axis. So let me just make it like this. Okay, great. Now we know that EQ is pointing in this direction. This is our EQ, and our E minus Q, that is pointing in this direction. So this is our E minus Q, right? And this is our angle theta over here, and this is our angle theta over here, as per the diagram, as we can see. And E net is pointing along x-axis. Okay, so we can split these EQ as, in this side the component of EQ will be EQ sin theta, and in this side it will be EQ cos theta. And E minus Q, we can point it here in this direction, E minus Q sin theta, and the component of that will be this side as E minus Q cos theta. So this will be the way we will make use of, though you don't have to draw the second diagram in board exams, right? You have to only draw the first diagram. Okay, and let's see how to proceed. Let's find the magnitude of EQ. Now if you remember that electric field of any charge is given by K Q by R square. That's the electric field. So let's use the simple concept for our first charge, that is positive charge E plus Q. Now E plus Q will be equals to K, which is 1 by 4 pi epsilon naught. We have discussed in the previous lectures. The charge is plus Q, and the separation here is AP square. And that we can write it as Q upon 4 pi epsilon naught. And AP is nothing but root under, so squaring the root will go, and it will be R square plus A square. I hope this is clear. EQ. Okay. Similarly, let's figure out E minus Q. So E minus Q over here, that will be equals to same. We will make use of same above formula, 1 by 4 pi epsilon naught. Again reminding you, the negative sign is not considered, so it will be Q by BP square. Exactly. So BP square. So BP, which is again the same value, it will be Q by 4 pi epsilon naught R square plus A square. I hope this is clear. Okay, EQ is clear and E minus Q is clear. Now looking at EQ and E minus Q, we can see that both of them have the same magnitude. Yeah, both of them have the same value, Q by 4 pi epsilon naught R square plus A square. Now looking at the second diagram, which is this diagram, what we can say here is EQ sin theta, which is pointing in the upward direction over here, and E minus Q sin theta pointing in the downward direction. Two equal and opposite directions, and magnitudes are equal, right? So these components will cancel out. So no role of sin theta, both cancels out, right? So net electric field will be here, will be E net. Let's write it as E net, and that will be our EQ cos theta plus E minus Q cos theta. Only the cos components will survive because sin theta are cancelled out. Why? Magnitudes are same and directions are opposite. It's like at two forces, if somebody is pulling a table from one side with 10 Newton and another side also 10 Newton, the table will go nowhere, right? Because equal and opposite forces will cancel out. Now, EQ, we know that it's 1 by 4 pi epsilon naught and Q over R square by R square plus A square cos theta. And E minus Q is Q by 4 pi epsilon naught R square plus A square cos theta. Now 1 apple plus 1 apple, so 2 apples. So this whole thing is same, repeating itself. So 1 apple and 1 apple will add, and that will give us 2q cos theta whole divided by 4 pi epsilon naught R square plus A square. I hope this is clear. Now if you look at our diagram, the first diagram, which is the most important part. For this diagram, our cos theta is nothing but base upon hypotenuse that we have learnt in class 10th. So which triangle to choose? Any triangle. AOP you can choose or BOP you can choose, doesn't make any difference. I am choosing the first one. You can choose the second one, you will get the same result. So base is AO and hypotenuse is AP. If you are choosing the second triangle, it will be BO upon BP. That will be similar. So AO is nothing but A. And AP is root under R square plus A square. I hope this is fine. This is our cos theta. Now this cos theta, we can substitute over here and we will get our expression for total electric field. That will be 2q upon 4 pi epsilon naught R square plus A square. And let me just separately write the cos theta value as A upon root under R square plus A square. Now this root under r square plus a square, we can rewrite it as r square plus a square power half, because root is half. Here the power is half and here the power is 1. When you multiply both, the powers will add up. And that will be 4 pi epsilon naught r square plus a square whole power 3 by 2. Now that will not be our final expression. We'll just make a slight change over here. 2aq. What is 2aq? So 2aq is a dipole moment. We have learnt in the previous lectures. 2aq is dipole moment. So dipole moment, when I explained, I gave you the direction. Dipole moment always points from negative to positive. Always. Now look at the direction of dipole moment. Dipole moment is pointing from negative to positive. Electric field is pointing from positive to negative. So we will put, when you express it in terms of dipole moment, we will put a negative sign here, because it is pointing in the opposite direction to the direction of net field. So from there this negative sign arrives, and this will be r square plus a square whole power 3 by 2. Any doubt up till here? Now, this is our actual electric field, but we will use a assumption that if we are finding very far away from the dipole, the electric field on the equatorial plane, then r will be much greater than a. And in that case, if r is much greater than a, then r square plus a square, that will be approximately r square. Let's substitute this value in this electric field. So E net will be equals to minus P whole divided by 4 pi epsilon naught r square plus a square, that will be r square whole divided by 3 by 2 power 3 by 2, and that will be minus P whole divided by 4 pi epsilon naught square and 2 cancels r cube. So that's our E net for a equatorial plane. So two most important things you have to understand here, that for a dipole on the equatorial plane, it's minus P by 4 pi epsilon naught r cube, and electric field due to the same dipole on the axial plane, that will be 2P, that we have discussed in the previous lecture, that is 4 pi epsilon naught r cube. So negative sign, and secondly here it is twice. So we can say that E axial, ignoring the negative sign, that's just a direction. So I am just taking the magnitude E axial upon E equatorial. That will be equals to 2. So axial, if they have given you equatorial value, you can simply multiply it with 2, you will get the equatorial plane. The red part which I have written, that you don't have to include it in the derivation. That is just an extra thing you have to remember for problems. But for derivation, you have to do in board exam up till here. Any doubt? You want to copy this? Okay, I'll move to the next topic. Let's see the next part. Okay. Let's see the next part. The next part is, okay, what we have discussed. Let's see a recap of what we have discussed in the previous lectures. Starting from the first lecture, I discussed that there are two types of charges, positive and negative. Let me remind you that positive charge is lack of electrons, negative charge is excess of electrons. Now, every charge has a field around it, and this field is responsible for an important part, which is force. And this force we have discussed as Coulomb's force, and this Coulomb's force gives you force between two charges at a time. That's very important, two charges, because students, they get confused that why we are making it more and more complicated, because at the end of the remaining topics, they will focus on something different. And when we reach to that topic, many students have this doubt that why we are dealing such situations. We already have Coulomb's force, we can simply apply the formula and we can get the solution. But the problem is, Coulomb's force works for two charges at a time, and when you increase the charges, it becomes more complicated. We have done such problems like for a triangle, for a square. So for 4 maximum in board, they keep 4, but even if it becomes 5 and 6, it takes more and more time, okay, to solve using Coulomb's law. Now then, after that, we discussed a special type of configuration, that is dipole. Now what's a dipole? A pair of charges, equal and opposite, okay, equal in magnitude, opposite in direction. Then we found the field due to dipole. Now why we found the field due to dipole on the axial plane and on equatorial plane? Sir, what if there is neither axial nor equatorial or any random point here? That is discussed in NEET and JEE, okay. that we will not discuss for the boards. So for equatorial and axial, they are unique positions corresponding to a dipole. Sir, what is a dipole in real life? A simple case of dipole is the salt, common salt, what we eat. So if you take NaCl, yeah, common salt, if you put it in water, Na plus and Cl minus, that's an electric dipole. You will get a positive charged sodium and negatively charged chlorine. Now that acts as a dipole. Now if there is a dipole, then there is a field around it that just now we have discussed, we have figured it out, right? So if there is a field around this, if you place a charge around this dipole, how that charge will behave? That's important. So if you know the field, you can figure out the force, right? So that was the concept of field. Now next topic is, third important topic related to dipole is dipole in an external electric field. Now if somebody is giving an electric field and if you place a dipole, what happens in that case? So dipole in an external, and what's important about this topic is it's a uniform field, external uniform electric field. That's a very crucial thing, uniform electric field, because if it is non-uniform, things will be little different, and that is not there in our NCERT, right? So we will focus ourselves on uniform electric field. So what's a uniform electric field? A uniform field will look like this. You have a constant value of field which remains constant and it doesn't change. If I completely fill this whole space with such a field, now you can't say that, though it looks like there are gaps, I am not putting these gaps, okay? So this is like a uniform electric field. All over the space, you can't say where is the value. Okay, now since I have colored it on, so it became little dark, but it is uniform, so the value will be same, okay? Okay, and if there is a field, now sir, who is applying this field? Maybe some charge, we don't care about that charge, but what we care about is, we know the value of this electric field and that is fixed. That's why it is called uniform. So at each and every point, if I place it here, if I place it here, every place the field is constant, it is not changing. Can you give a particular example like 2 Coulomb, Newton per Coulomb or 10 Newton per Coulomb, any charge? Who is applying that? We don't care. We just care about that what is the value of electric field in this region, right? In such a region, if I place an electric dipole, let's say this is a charge plus Q and let's say this is a charge minus Q. And this charge is oriented at any angle. So let me just make it 1 second, little specific. Okay, so this is our dipole and the separation for this dipole is 2a. And let's suppose the direction of electric field is pointing in this direction. It's constant, all over constant, right? If I draw an electric field line over here, we can see that the dipole is making an angle theta with the electric field. And because of this theta, there will be something important which we will see. So just imagine that this is a magnetic field. Just imagine, because we have done that in 10th standard, this is a magnetic field due to a strong magnet. And we are putting another magnet which looks like this inside this field. What will happen? So this will rotate. So why it will rotate? Let's see. Let's see the core concept. So if electric field E is positive, this plus Q will repel it. So it will repel, let's say, in this direction. Right? And with what force? F equals to QE. That will be the force of this positive charge. If positive charge is repelled by the electric field, the negative charge will automatically attract, because that's in opposite direction. So that will be F equals to QE. Sir, why not negative? We are taking magnitudes. Direction is already given, right? Now, if I'm just reminding you the concept of 11th standard so that you can understand it better. If this is a table, I am applying a force of 10 Newton in this direction. Another person is applying a force of 10 Newton in this direction. Where will the table go? So it will go nowhere. It will remain there. Great. If this is the same table and instead of 10 Newton, I am just putting here 5 Newton. Where the table will go? So it will move in the upward direction. Yeah, and if I make this as 25 Newton, then it will go in the downward direction. Great. Now what is important here is this 25 Newton and 10 Newton are pointing in the same direction. What if the same table is here? Be very careful. I am applying a 10 Newton force in this direction and somebody else is applying a 10 Newton force in this direction, but provided it's not in the same point, the point of action is not same on the table. One is on this extreme end and another is on the other end. If some force acts like this, when it is not acting in the same point, though it is in the opposite direction, but it is not acting at the same point, what the table will do? What's the natural tendency? Sir, it will try to rotate. And this rotation is because of a new concept which we discussed in 11th standard, that is torque. So the same situation happens for this dipole. When a dipole is placed in an external uniform electric field, it experiences torque. It experiences torque. And torque from 11th standard is nothing but torque tau, that will be equals to force into perpendicular distance, or more being specific, R cross F. Where R is the perpendicular distance along which, like if this is the length of the table, that will be R, being more specific, and force is the value, magnitude which you are applying here. So in this case of dipole, R is nothing but 2A and F is nothing but QE. Any doubt in this part? Now 2A into Q, 2A can be directly multiplied with Q. We can pair it up with Q. Why? Because Q is a scalar quantity. You can take it. So we can't directly make it as 2AE, but we can make it as 2AQ cross product with E. Be very careful, this is not multiplication, this is cross product. So 2AQ is nothing but P cross E. And P cross E is nothing but PE magnitude. I can put here two magnitude signs, and here it is sine of angle theta, where theta is what? So theta is the angle between the electric field and the perpendicular direction, or the direction of the length of the dipole. Great. So sir, what happens if theta becomes 0 degree? If the dipole is aligned along the field, then theta will be 0. So let me just write here, if theta becomes 0 degree, sine theta will become 0. And in that case, the torque will be 0 experienced by the dipole. If the theta becomes 180 degree, just opposite, then sine 180 is again 0. So torque again will be 0. What about theta is 90 degree? If theta is 90 degree, then sine theta will be 1. That's the maximum value of sine. And torque will be maximum, in this case PE. That will be maximum, I am writing here. So they can ask you, when will a dipole will experience a maximum torque? Theta is 90 degree. Now that's, I think, enough for boards. But now looking at the papers this year and all, we can say that we can understand one more very small concept, that what happens if instead of uniform, it's a non-uniform field. So which means the electric field at each and every point is different, right? So let me write here only one statement. I am just putting it extra in by any chance if they ask for a non-uniform electric field. For a non-uniform electric field, electric field value at each and every point will be different. So if electric field value is each and every point is different, then the force experienced by this minus Q charge, that will be different from the force experienced by the plus Q charge, because the electric field values are different, right? And in this situation, there will be two things happening along with the torque. Force will be experienced. Along with the torque, a force will be experienced. That will be the case in case the field is non-uniform. That will be very important case for NEET and JEE. Any doubt in this part? I'll remove this. I'll move to the next part. Let's understand the next concept. And our next concept is of, okay, so up till here we discussed about charges like 1, 2 or dipole or 3, 4 maximum charges. Now we will not count it like that. Now we will have continuous charge distributions. We will call it as continuous charge distributions. let's understand what is continuous charge distributions. Okay. Because in real life, we mostly find continuous charge distribution. We don't find single charges. Okay, because there are millions and millions of charges which are moving. Okay, we have discussed this in the first lecture, that when 1 ampere or 1 coulomb of charge is transferred, we say that 6 into 10 raised to 18 electrons are transferred, right? And 6 into 10 raised to 18 is enormous, right? So continuous charge distributions are the scale at which we are dealing in the real life. So give an example. For example, number of hairs on your head, that is continuous. You can't count. Now that doesn't mean they are infinite, right? They are finitely infinite. So finitely infinite means something which is uncountable, but still we can count if we have that much of time, right? Yeah. So continuous charge distribution is somewhat like this. Like if I take a metal sheet and I completely charge it. Now I don't know how many charges are there, but we can draw it like this. There are a lot of charges are there. Lot of means a lot of. Like the number of stars in this space. So can we count stars? Of course you can count stars. For that you need to do graduation in physics so that you can understand what are the statistical methods in which we can count stars. Right? So if you take instead of sheet, if I take a rod, this rod is completely charged. If I take a spherical ball, this is completely charged. So such distributions are known as continuous charge distribution. And in continuous charge distributions, there will be mostly 3 cases. The first case is, we call it as linear charge distribution. Linear charge distribution. If the charges are along the length, let me write the definition also. If the charges are present along the length of an object, such distributions we call it as linear charge distribution. Any doubt? Next is surface charge distribution. Surface charge distributions. If the charges are present along the area, if the charges are present along the area, like a sheet. Okay, I'll refocus on these things. Let me just write the definitions. Volume charge distribution. If the charge are present along the volume. Now, be very careful when you are dealing with these 3. You can simply see that this is 1-dimensional, this is 2-dimensional, and this is 3-dimensional. Though our course focuses mostly on 1D and 2D, though we will discuss 3D also, a little bit 3D, but numericals mostly bases on 2D, right? So we will focus on these things, 1D, 2D, 3D, 1-dimensional, 2-dimensional, 3-dimensional. But in real life, if we focus, there is nothing known as 1D and 2D. Because if you look at a simple wire, this wire itself has an area of cross section. So that's a 3D, right? Because that's why we can simply hold it, okay, we can cut it, we can do anything, because that's a 3D, it's not a 1D. But what happens that if wire we are taking, considering like in the line which I have drawn here, it looks perfectly 1D because the length is more prominent factor other than area and any other parameter, right? So charges are mostly distributed along length. Now similarly, if I take a paper sheet, the thickness, if you ignore the thickness, because though thickness is negligible compared to the area, so the length and breadth becomes prominent but height becomes negligible. So that's a 2D. Similarly, if you take a 3D, it will be a cube or cuboid. Length becomes prominent, breadth becomes prominent, height becomes prominent. But be very careful. Students have this such kind of questions that, sir, why 1D? We don't have 1D in real life. Though you don't have, but the charges are mostly distributed along the length. The area of cross section is negligible. So we don't care about that when we are taking it as macroscopic variable, right? So be very careful with this. So if the charges are present along the length, we call it as linear charge distribution. If the charges are present along the area, we call it as surface charge distributions. And if it is present along the volume, we call it as volume charge distributions, right? So depending on these types of distributions, we have one more thing, and that is called as density. Before that, I'll explain you the concept of density from very basic 7th standard. Okay. So let me recall the concept of density. If I take a piece of stone, let's say this is a stone, okay, and let's say this is a wood, a log of wood. Now we can see that log of wood is looking much bigger than the piece of stone. If I take this both and place it in water, I throw it in water, we know that the wooden log will float while this will sink. If I break the stone into two pieces, again the two pieces will sink. But the log, if I make two pieces, again they will float. So the question is, what is the difference? Looking here, the mass, I can take it of 5 kg and I can take the mass of this as 2 kg. Even I can take it as 0.2 kg. Small, I am taking a small piece of stone or pebble and putting it in water, it will sink. So the mass is not a factor. If I look at the volume of this one is large compared to the volume of this one, which is very small, right? Still, volume is not a prominent factor. So what is important here is density. So what is density? Density we have learned as mass by volume, right? Now I am being very specific, more specific this time, because I am calling it as mass density, because we are dealing with mass. How mass is distributed in a given volume. Sir, how to imagine that? Imagine a classroom. Imagine the classroom in which you are attending the class in your school, and there are 50 students in your class. Great. Now keep the classroom as same, don't change anything, and put here 500 students. What will happen? So the volume is same, mass is changed, and the density increased, because the volume in which the people are packed is very high. And in such situations, the density increases. And in that case, the same thing happens for the log and the stone. The wooden log, what happened? When you break it into 1 million pieces, each piece will have those molecules which are loosely packed inside the given volume. But in this case of stone, they are very tightly packed in a given volume. That's why the density is very high. Now let's try to understand it in mathematical way. If I look at the density of a log, let's say, so for the log, the density of log, let's say, I'm just making it as 5 by 10. So when the mass was 5 and the volume was 10 meter cube, the density is half. If I increased the mass to 500 and made here as 1000, again the density remained very low, 1 by 2. If I made it at 10,000, let's say, the mass, very heavy log, whole divided by the volume also automatically increased, 20,000. Still, the density remains same. So, density is a factor which remains constant for a given object. Understood? So, keep in mind this concept. Let me come back to our distributions. So, if you are dealing with linear charge distribution, one prominent factor which remains constant, and that is called as linear charge density. Now be very careful. Previously we discussed about mass density. Here it is charge density. So linear charge density will be denoted by lambda, and that is nothing but how the charge is distributed in a given length. So sir, you mean if I take a wire, what factor remains constant for this wire? Lambda. Charge will be different. Length will be different, so, but it has a fixed length. Okay, so if I take this wire and if I cut this small part A, if I take this long part B, or if I take the remaining wire part C, A part is very small compared to B and C. The amount of charges present in A will be very less compared to B and C. Yes, sir. The length of A part is very small compared to B and C, of course. But what is constant for this wire? Lambda. So, lambda of A will be equal to lambda of B will be equal to lambda of C. That's an important property of linear charge density. Similarly, if we call as surface charge density, what happens for surface charge density? If I take a sheet and if I take this small area, this huge area and this very big area, for each one, what remains same? A, sigma B and sigma C. Sir, what's sigma? Surface charge density is denoted by sigma and that will be equal to what? Charge present in a given area. Okay. Similarly, if I go for the third case, that is volume charge density. The volume charge density is denoted by rho. Now be very careful, mass density is also denoted by rho. Okay. So don't get confused, and sigma is a parameter which is used in different contexts. So just don't generalize it that sigma always means charge density. No. Later at sigma in the third chapter we will make use of sigma as conductivity. Be very careful. So don't. There are only in physics, whole physics, there are few symbols there are fixed, like H, Planck's constant, which you have learned in chemistry also last year, C, speed of light, and universal gravitational constant, that is G. Other than this, all symbols are used randomly in different places. So don't get confused with that. No. Just to no particular reason. Okay, there is no particular reason. Okay, so rho is given by, similarly we can make a relation for volume, charge present in a given volume, that will be our volume charge density. Now, since we have for JE also, and a little bit of our NCERT also focuses on this, so we will just make it as delta. Delta will make, so that later we will, when we integrate it or differentiate it, it becomes quite easy for us. So delta Q by delta L, delta Q by delta A, and delta Q by delta V. Because Q we assume, sir, why delta? Because Q we assume that the total charge, like in this sheet, if the total charge is Q, then for this part it will be delta Q. Small part of section of delta Q is charge, and in that section the area is delta A. So these are the three relations, very important. Sir, what about units? Charge per unit length charge is coulombs, length is meter, so coulomb per meter. And here the charge is coulombs and area is meter square, so coulomb per meter square. And here it is Q is C and delta V is meter cube. We can find the dimensions. I will not focus on dimensions this year a lot because dimensions is a part of 11th standard, but though they ask in board exams also, right? But what they ask, mostly those dimensions we will cover it. Okay, here you can make it yourself. Okay, coulombs is 80 and meter is length. Okay, so that we can see it. Okay, so here this is called as continuous charge distribution. A lot of continuous charge distribution parameters we will discuss in that's our remaining part of the chapter tomorrow. First, let's do some problems based on our these topics which we have discussed. Okay. Yeah, so the correct answer for this one is electric field lines can never cross each other. We have discussed why they can't cross each other. Let's see the next one. So electric field lines for a negative charge is radially inward. That's an important thing. Done. Let's see the next part. Says a pair of 2q and minus q charge separated by a distance 2a can assume to be an electric dipole. No, we can't. Why we can't? Because one is 2q and one is minus q, right? Their magnitude should be equal and opposite, right? So the correct answer is no. It says the unit of electric dipole moment is Coulomb meter. So correct answer is option C, Coulomb meter. Newton per Coulomb is electric field, Coulomb is charge. So correct answer is C. Electric dipole moment is a vector quantity because I have specifically said that the direction is always from minus q to plus q. And that we have discussed in today's lecture also for equatorial plane. At the end, we put a negative sign because of this vector quantity. If it was not vector quantity, why we will consider the direction, right? So correct answer is vector quantity. The question says unit of electric dipole moment is dBi, Dyn, Pascal and none. So this was a PYQ from CBSE once. dBi is another way of saying Coulomb meter. Okay, dBi was a scientist, in honor of him. dBi is a unit. Dyn is force and Pascal is pressure. Okay, so correct answer is option A, dBi. See. So question says over here, two charges 10 microcoulomb and another minus 10 microcoulomb are placed at 10 millimeter apart. The electric dipole moment of the set of charges. Now let me remind you, the formula for electric dipole moment is P, that is equal to 2AQ. And let me just give you a small idea again, that it is Q over here and it is minus Q over here, and the separation itself we take it as 2A. So Q here is nothing but 10 microcoulomb, so we can just make it as 10 into 10 to the power minus 6. And the separation 2A, be careful, very common mistake students do. 2A itself is 10 millimeter, don't multiply it with 2 again. So 10 into 10 to the power minus 3. So P will be simply 2AQ, that's our 10 into 10 to the power minus 3 into 10 to the power minus 10 into 10 to the power minus 6. 100 into 10 to the power minus 9, and that's 10 to the power minus 7. So correct answer is 10 to the power minus 7 Coulomb meter. That's our option B. Yeah, the question says direction of electric dipole moment is from negative to positive charge. That's the direction. So the electric field of an electric dipole is proportional to the distance as 1 by r cube. We have found this for axial as well as equatorial, right? For generally for a single charge, it's 1 by r square and 1 by r cube for dipole. So question says here, a pair of two charges plus q and minus q separated by distance a will have its dipole moment. Now we know that dipole moment P is nothing but 2AQ. But the 2A is separation between q and minus q. But the question itself is saying the separation is A. So the correct answer for this will be AQ. Be very careful with this. Let's see. So two charges, one 5 nanocoulomb and another minus 5 nanocoulomb are placed 1 millimeter apart. The dipole moment will be how much? So first of all, let me write here Q is given as 5 nanocoulomb, 5 into 10 to the power minus 9 coulomb, and placed at R is equals to, or let me just make it as 2A instead of making new symbols. 2A is 1 millimeter apart, so 10 to the power minus 3. So we know that dipole moment formula is nothing but 2AQ. So 2A is 1 into 10 to the power minus 3 and Q is 5 into 10 to the power minus 9. So that will be 5 into 10 to the power minus 12 Coulomb meter. That's our option. Okay. Let's see the next one. The question says an electric, now be very careful, I have already explained you how to proceed a problem. What happens is majority of the students, they just read the question and then they think that how to proceed. First thing is, always when you read it, write the parameters. That will give you a direct hint. So question says an electric dipole held at 30 degrees. So theta must be 30 degrees. Straight away write it. If you will not write and just read the question, majority of times you know the things but you will not be able to solve it. So theta is 30 degree. With respect to a uniform electric field, E, which is equal to 10 to the power 4 Newton per Coulomb. Great. Experiences a torque. Tau is 5 into 10 to the power minus 8 Newton meter. And what they have asked, a dipole moment P. Now we today itself, we have seen that torque tau is nothing but Pe sin theta. We know that. Let's plug in the values and P will be equals to tau by E sin theta. And tau is nothing but 5 into 10 to the power minus 8. E is nothing but 10 to the power 4. And sin 30 degree, that's half. We will put the values. So 4 taking on the top, it will be 5 into 10 to the power minus 12. And sin 30 is half, so let's take the 2 on the top, it will be 10 into 10 to the power minus 12. So Coulomb meter, and that's our dipole moment P, which is option C.